Welcome to MEI Mechanics. We're on the topic centre of mass, and this is video 1.6, centres of mass and equilibrium. Now, just to introduce this, let's remind ourselves about the shape that we looked at in the previous video, this 3D shape, which was a composite shape made of a cone and a hemisphere. And by using the standard formulae to begin with to find the centres of mass of those two individual shapes, we could then combine those and find the centre of mass of this composite shape, and it was roughly located at this point here. The main thing to notice in this case is that centre of mass, as well as being on this horizontal line through the vertex of the cone, because that's an axis of rotational symmetry for the shape, it also happened to lie on this side of this this plane which separates the cone and the hemisphere. So it was on the cone side of that. And that's important when we ask ourselves this question, which is what happens if we rest this on a smooth horizontal surface? Well, the point which is in contact with the ground is here, and because the centre of mass lies to the left of that point, so the centre of mass is there, well, that's where effectively the force on the object is acting. So that force is acting downwards, because we're talking about gravity here, so it's acting downwards, and so there's a turning moment on the shape about this point here, and that means that the shape will want to fall and rest along the cone side of itself. If the centre of mass was on the other side, then it would try to tip the other way. So the place at which the shape is going to want to be in equilibrium is going to be determined by where the centre of mass is. Now, the most common type of example that you're going to see is where an object is being suspended and hanging from a piece of string, for example, attached to the shape at a certain point. So that will be the point of suspension. That's the point at which the shape is connected to the thing it's hanging from. And what will happen is the centre of mass will always end up lying on the vertical line down from the point of suspension. So if you have a nice simple shape like a rectangle, if we suspend that from, say, point A, then the centre of mass, which is right in the centre of the shape, will be directly below point A. In the case of a triangle, the centre of mass lies roughly here, so that's 1/3 of the way up from there, 1/3 from the right, if you remember from that video. If we suspend that from point A, then it's going to look something like that. So that centre of mass, which is around about there, is directly below point A. So this is the type of thing that you're going to have to deal with, though, not just a simple shape, but a composite shape, rather like some of the shapes we've met earlier. Work out where the centre of mass is, and from there decide what is going to happen when it's suspended from point A. And this will be asked in the form usually of an angle. So what angle does a particular side make with a particular direction, usually with the vertical? Okay, so the first stage is going to be to calculate the centre of mass. And if we remember, there's quite a nice way of doing this. So we'll divide the shape into 3 simple pieces, 3 rectangles. We'll locate the centre of mass of those individual pieces. Because they're rectangles, they'll just be at the geometric centre of those rectangles. And by thinking about the area of these, we can write down something which is proportional at least to the mass. So if we call this part A, this part B, this part C, then for part A, the mass, well, it's 3 centimeters by 1 centimeter, so it's got an area of 3, and so the mass will be 3k, where k is a constant. The x coordinate, well, let's stick to our convention of using the bottom left as the origin. Then the x coordinate of A is halfway along. It's 3 centimeters long, so that's 1.5. The y coordinate will be 0.5 from the base of this rectangle and then we have to add that on to a 3 and a 1, so that's 4.5. And then we multiply each of those by the mass, so 3k times 1.5, that will be 4.5k, and then 3k times 4.5 will be 13.5k. And then we can keep going in this manner. So having done that for all three pieces, we then find the total of the coordinate times the mass for the x coordinate and the y coordinate, and then divide each of those by the total mass, and that gives us the coordinates of the centre of mass, which for this shape turns out to be 1.4 to 0.3. And as I say, that is from the origin at the bottom left. So if the origin is there, 1.4, so that will be somewhere to the right of this line, and 2.3, well, that's 5, so it'll be a little bit below halfway along this, so we're talking somewhere around about there. Right, centre of mass. Interesting, the centre of mass here is not actually within the shape itself. That can often happen in shapes like this. The centre of mass is there. So if this is to be suspended from point A, then this line between point A and the centre of mass, that's going to end up being vertical. And so the angle that we're interested in is going to be this angle here. Okay, now in order to work that out, well, we need to think carefully about firstly where that centre of mass is. That's 1.4, 2.3. So that means that this length here is 1.4, and then that's forming a right angle triangle there, and that length is this whole 5 minus that 2.3, so that's 2.7. All these units are centimetres, of course. Okay, so then it's just a case of using trigonometry. I can see that the tan of that angle will be 1.4 over 2.7. So do the inverse tan of 1.4 over 2.7, and that will give me the angle that I require. So there we are then. The tan of the angle is 1.4 over 2.7, giving an angle of 27.4 degrees, and we can see that on our diagram. The centre of mass was around about there. We can now see that that is the vertical line, and this angle here is 27.4 degrees. So that concludes video 1.6, centres of mass and equilibrium, and concludes the topic centre of mass.